Welcome to class today. So today's class is really about understanding how we see this blue pen and how we know where it is. So it seems almost trivial, but if you really start to think about it, it's a complicated question, and it took thousands of years for people to figure out how this actually worked. So we all know there are a few key elements, all right? So there are really three things that must happen for me to see this pen, right? Thing one, there must be light. Hey, the lights went out. I don't see the pen. Now, this must seem really obvious, but I don't see the pen now. Why not? Because there's not a pen there. Now the pen is back there. So I need a source of light. Somehow the pen needs to be there, and the light needs to somehow interact with the pen. We'll talk a little bit more about that in a few moments. And then right now, I don't see the pen. You probably, like, well, Mr. Owen, open your eyes. All right. So somehow there needs to be light. It needs to hit the pen. And then the third thing is that light that bounces off of the pen somehow must go to my eyes. And we won't get into how our eyes work and our brain interpreting that signal from our eyes. But the key ingredients are a source of light, an object which the light can bounce off of, we'll use the word reflect off of, and a way to detect that light that bounces off, which we have on our face, which is our eyes. We could also use cameras to detect that. Actually, you're seeing this pen through a camera now, not through my eyes, but all of those elements must be there. Okay, so here we can see an artistic rendering of what I had there. Okay, so the first thing that I have is a light source. Now, hopefully you realize light goes off of this light source in all directions, but some of that light will hit the pen, all right? Now we're going to talk about ways that the light could bounce off of an object, but for now we'll assume then that light bounces off the pen, and some of that light that bounces off of the pen gets to my eye, all right? And that's how I'm able to see it. So those three things must be present. Okay. What I want to focus on first, though, is the way the light that hits the pen interacts with the pen. So let's zoom in on what happens here. When light hits an object, three things happen. Okay. Some of the light is reflected. That's the light that we can see. Some of the light can be absorbed. Right? So that is light that won't be reflected, all right? And then finally, light can be transmitted. Now, in this case, light doesn't really pass through the pen, but this would be, an example would be a window. Most of the light, most of the visible light is transmitted through it. If it was a colored window, some of the light might be transmitted and not others. But those are the three things that can happen. All right, and it's just real easy to remember. You can remember it to rat, okay? Or if you prefer, some of you might like art, or perhaps you really like tar. Well, not tab, tar, okay? Or maybe you like rata, or maybe atra. I don't think too many people will remember this. I usually use rat in order to remember what the three things are that light can do. Now, it's important, these three things in combination are the reason why I see a blue pen. Hopefully you understand, we're not going to cover it in much detail now, but light, if you run it through a prism, has bands of color, right? We're not going to, I can actually use some fancy colors, okay? So down at this end of the spectrum, we have some reds, right? And if we keep on going, you might end up, it's a gradual change. But you'll kind of go from reds to orange, and then you get yellows. The yellow doesn't look too much different than the orange. And then you get, let me go back to here. Maybe there were better yellows to pick. This yellow might be better. Let me put that yellow in. Okay, and then It's all gradual changings, but then you get green. And then you get, I probably should have spread this out a little bit more. And then we'll get, whoops, let me pick out some, we kind of get into the blues. We go into the greens and the blues. And then we kind of get purpley down at the other end of the spectrum. It was, let's see, I think we have sort of indigo colors in here. So I think indigo kind of is maybe something like that. All right, and then the colors end up being a little bit more violet by the time we get out at the end. And maybe you even learned that this is red, orange, yellow, green, blue, indigo, violet, or Roy G. Biv. Now, Newton actually came up with this nomenclature. It's kind of ambiguous where we go. A lot of people just say we go from blue to violet, but it's easier to remember Roy G. Biv than Roy G. Biv. So we'll go with those being the colors of the spectrum, but it's really a continuity of color from red up to violet. So what happens when I see a blue pen? Right? If I'm going to see a blue pen, it means this part of the spectrum the light that hits the pen, which is all of these colors combined as white light, must have a lot of this reflected. Given that light doesn't really pass through the pen, I guess some of this, the plastic is somewhat clear, but all of these other colors in the white spectrum are basically being absorbed because it's a fairly solid color pen. Some of it is actually being transmitted because it is a bit translucent, but it's mainly being absorbed. There's literally the light that's coming in is interacting with the molecules of the plastic in the pen, and it has some dyes in it so that it absorbs light. We'll later on maybe talk about the wavelengths of the light. It will absorb the wavelengths in the red up through the green and a lot of those violets so that you predominantly see blue colors coming out. By the way, in your eye, you have three cones, and those cones correspond to the reds. There's a cone in your eye that is good at detecting green and light near the green. And there's a cone in your eye, this is back on the retina of your eye, that absorbs blue. All right. And it turns out, you all know in art class that if you mix red and blue, you get purple. All right. And that's because if you're sort of in the violet end of the spectrum, the red actually gets excited by these wavelengths as well. So the cones in your eyes have pigments in them that absorb colors, and the red cones in your eye also kind of have a second peak, a smaller peak up here at the violet end of the spectrum. So when you see red and blue together, it kind of corresponds to seeing things up there in the violet end of the spectrum. So you know that with a television, you can just use, hopefully, just red, green, and blue LEDs in order to produce all of the colors that you need, because they're stimulating those cones in your eyes in different proportions in order to generate all the colors that you might want. In MATLAB, you can create any color you want by writing it as a vector. So if I write something like 0.5, 0.4, and 0.2, we have a lot of red, a fair amount of green, and not much blue in that color, and you can produce any color of the spectrum in that manner. So the final thing I want to cover in this video are the two types of reflections that we could have. So let's pretend we have a light source out here, and let's have maybe a wall here, and we're going to put a little mirror over here. Okay, so light coming off of the source, we'll use a red line, could hit this mirror and basically bounce out. There's something called the law of reflection, which says that if I put a normal line to the mirror, the angle at which the light bounces off the mirror is the same as the angle of incidence. The angle of reflection, that would be measured here, angle of reflection. And over here was the angle of incidence. And there's a physics formula, it's not much of a formula, that simply says the angle of incidence equals the angle of reflection. You might wonder why we don't just measure the angles out here. You could, but it's easier when you're talking about a plane, which a mirror is actually a plane in 2 dimensions, to talk about a line that is normal to the plane. So it's easier to measure in physics and math terms the angle relative to that normal rather than the angle relative to the plane, because the plane extends in a lot of different directions. Well, in 2 dimensions. Now, if I were to put a couple people over here, now I'm not going to draw the whole person, I'm just going to draw their eyeballs. So let's say over here is Susie. So Susie's eyeball is over here. And over here, this is where Bob is sitting, okay? Susie and Bob will not see the light coming from the source. Or if that were light coming from, I could put a source of light, or I could even have another object here. And there could be light bouncing off of this object, hitting the mirror and bouncing out again. They wouldn't see it, okay? But right here, this could be, Sarah, okay? Sarah's right there. Sarah would be able to see the light that's bouncing off of the mirror, okay? This kind of reflection is called a specular reflection, where the light is coming in. It's actually lots of rays of light coming in and bouncing off of the surface in a very smooth, organized way, okay? But the surface of a pen is not like the surface of the mirror. If we were to look closely at the surface of the pen, it's actually quite, it would be quite rigid if we look at it under, an electron microscope or something like that. There's a lot of rigidness to it. Okay? So if we have, let me go back to this picture here. If I had a couple parallel beams of light, so I put one beam in. If another beam was right next to it coming in parallel, it will bounce out parallel. So all the light coming in from one direction will head out in the same direction. But the surface of most objects are rough. Down to kind of a almost molecular scale. So if I had one beam of light coming in from over here, it might hit and bounce way over there. Another beam of light that was coming in from the same direction and hits there might bounce out like that. And here's another one coming in. Who knows what that's going to do. Maybe that one goes, well, probably not quite like that, but they all come in from the same angle, because they're coming in from some source over here. They're all coming in parallel to each other, these light rays, but they bounce out in all kinds of directions. Now that's important because if I hold up the pen, everyone in the room would be able to see it, okay? So let's put Bob back in here. Bob could see it if he were sitting right here. Maybe Susie was here. She can see it. And sure enough, Sarah can see it. If I were in the classroom, if I hold up a pen, anyone who's awake will see the pen. So that's because this is a diffuse reflection. The key is the light scatters. Yeah. We talked about the light is either transmitted, absorbed, or reflected. So we're specifically talking about just the light that's being reflected. It will reflect out in many directions. And that's why everyone in the room is able to see the pen when I hold it up, because light coming in from pretty much any direction, or light that hits it, will scatter to all corners of the room.